Okay, so just a couple of announcements. Oops, dog is trying to get out. Okay, sorry, just a couple of announcements for the class. So this is the last week on sort of finite group theory. So just as a reminder, next week is sort of, it's like a bridge week between the first part, which is all sort of about finite group theory and abstract group theory, and the second half of the class, which is about Galois theory and representation theory, which are really about thinking of groups as sort of symmetries of interesting objects that we want to understand, and sort of then using group theory to understand like these other objects that we actually care about. So next week, yeah, we're going to talk about the character theory of abelian groups. So it's a little bit ambiguous sentence that I just wrote down. So let me say this week is the last week. On finite group theory. And next week, we're going to talk about the character theory of abelian groups. And we won't go into depth on this, but like that includes Fourier theory. So like if you've studied Fourier series or like Fourier integrals, the Fourier transform, like that's sort of properly lives in the field of character theory of abelian groups. It's also interesting for finite abelian groups. So on cyclic groups, you get sort of an analog of classical Fourier theory that we'll talk about. And character theory of abelian groups, like that means representation theory of abelian groups. So abelian groups sort of, abelian groups, if you think about them acting by symmetries on linear spaces, like you can sort of break those down into irreducible components, sort of the building blocks, and the building blocks are all sort of one-dimensional. The one-dimensional representation is called a character. So this is sort of just how abelian groups act by symmetries on one-dimensional spaces. So that's sort of the connection to representation theory, which is the last topic we'll hit in the class. That's the last few weeks of the semester. But it's also one of the results we'll prove next week is sort of, it doesn't look at first like it has anything to do with Galois theory, but it's actually like the basic technical lemma that makes everything run in Galois theory. So one of the results we prove next week we'll come back and use to establish the main results in Galois theory. So that's why we're doing this now. But let me point out, this stuff will not be on the exam. So the material we're covering next week will not be on the exam. So the exam will only cover up through the end of this week, which is essentially chapters 1 through 6 in Gummin and Foote are the homeworks from week 1 through week 5. So there will still be a homework, but the homework will only have exercises. And I'll try to keep it short so that you have time to study for the exam as well. So the exam is the following week after that character theory week. So when I say the homework will only have exercises, I just mean there's not going to be sort of one of these problems at the end that you have a chance to rewrite and turn in again. In particular, so some people have asked me about this, so let me make sure I say it. So the rewrites of problems on homeworks 1 through 5 should be sent to me by email by 11:59 p.m. on March 4th. So 11:59, or March 4th is the day of the midterm. Okay, so you don't have to finish them. If you're rushing to finish, you don't have to finish before the midterm. You can finish after the midterm and email with me. And just sort of all in sort of one PDF in one email. just when you're typing out, you just clearly indicate for each problem like which week it corresponds to. So I know, but just include them all in a single PDF. Okay, so good. I think that's. Oh yeah, last in the exam, and it will be in class. I haven't totally figured out what that's going to look like yet, so I'll give you some more information about what the exam will actually look like. I guess next week. Are there any other questions? Okay, so we'll get going. So, so what we're going to talk about today are really groups built out of abelian groups. Okay, and so well, we're going to look at two different kinds. So let me just draw the diagram so we have it. So in the simplest groups are cyclic groups. And sort of inside of cyclic groups live inside of abelian groups, which is sort of the next simplest thing. I mean, in particular, any finite abelian group or finitely generated abelian group is just a product of cyclic groups. So you can either think of this step as sort of, at least if you are looking only at finitely generated things, to go from cyclic groups to abelian groups, you're just taking direct products. And that's not true if you're not finitely generated anymore. For example, the real numbers are not, like the real numbers are not sort of a product of cyclic groups, right, not of the rational numbers. But still, okay, so abelian groups, so at least in the finite generated place, are very close to cyclic groups. And then something we're going to talk about today are nilpotent groups. So these groups are no longer abelian, but they'll be very close to being abelian, and they'll have sort of a very canonical way to relate them to abelian groups. And they'll actually have a very nice structure theorem. So they'll have a structure theorem comparable to the structure theorem for abelian groups. And then these are contained in solvable groups. These are contained in all groups. So nilpotent groups, these will have nice structure theorem. And then solvable groups are somehow like, well, they're what you would guess if you're what these are sort of what you would guess I mean when I say groups built up from abelian groups. So a group is solvable if it has a chain of normal subgroups where all the quotients are abelian. So I'll write that down more carefully in a little bit, but so another way to say you have a solvable group, a group is solvable if and only if all of its Jordan-Holder factors are abelian. So this is something I basically skated by, but let me recall it now, at least out loud. So if you have a finite group, then it has simple factors. Like, so there are simple groups that are used to build that group. They're sort of canonically determined. And you get them just by induction. So you just like look at normal, you take a maximal chain of normal subgroups inside of it, and then just look at all the subquotients. And sort of if that chain of normal subgroups is maximal, that means sort of all the subquotients are simple groups. And it turns out there are lots of choices involved in doing that, but those choices don't change the collection of simple groups you get. So for example, if I look at the dihedral group of 6 elements or the symmetric group of 6 elements, same group, then that has a Z mod 2Z are a Z mod 3Z normal subgroup, and the quotient is Z mod 2Z. And so the Jordan Holder factors are Z mod 3Z and Z mod 2Z. And so that's an example of a solvable group because all of those Jordan Holder factors are abelian. Maybe write that here. And really the Jordan Holder factors are, well, they're abelian, and if you're in the, so if for these for finite groups, let me say, I should be careful here. A general group won't have Jordan Holder factors. This is something that exists for finite groups, but not general groups. But so if you're a finite group, then it's Jordan, sort of saying you're solvable, just saying the Jordan Holder factors are cyclic, which we can sort of write down more precisely. Or we can write this down in several different ways. Okay, so this is what we want to look at. And the reason, there are a few reasons we're interested in sort of groups built up from abelian groups. I mean, one reason is, well, I mean, you can think in terms of this like Jordan Holder program to classify finite groups. And if you think about that, then, well, we've talked a lot, and we've talked about simple groups, and we've talked a little bit about like how you can sort of start to classify simple groups. It turns out sort of studying solvable groups will give you a way to sort of, and there are some results about solvable groups that will let you sort of rule out the possibility of simple groups of many order. So that's sort of one reason to do this. But then also, like in this other part of the Jordan Holder program, where you're saying, how can you build, like, how can you start with simple groups and then build groups out of those? Like somehow the simplest setting you could do that in is the setting of abelian groups. You could say, start with abelian groups and look at how you can put them together. So it's a natural sort of first case of the second part of the Jordan Holder program to investigate. So that's sort of motivation just internally from group theory. Some better motivation is that solvable groups, they arise in nature in important ways. In fact, even the name solvable comes not from some property of group theory, but from some application. So the name solvable group comes from Galois theory. And so in Galois theory, you take some polynomial, like over the rational numbers, and then you attach some group to it, which is the symmetry group of its roots. And like that group determines some properties, some algebraic properties of the roots of that polynomial. In particular, that group is solvable if and only if you can express the, so this is something we'll talk about much more later, but a group is solvable if and only, a Galois group is solvable, the Galois group of a polynomial is solvable if and only if you can express the roots of that polynomial, sort of just taking, by iterating addition, multiplication, subtraction, division, and taking nth roots, where, like for any n. So this sort of, it comes up, and this is not exactly true, but somehow, in one sense, the origin of Galois theory is studying these solvability questions. This is one part of the origin of Galois theory. Like studying for which polynomials can you express the roots using only radicals. And like, and the big sort of classical result, and what we'll talk about is that for a general polynomial of degree at least 5, you can't. So there's no quintic equation. It's the same, and anyway, so that's where the name solvable comes from, is because this application of Galois theory. And similarly, I mean, nilpotent groups arise really naturally. So in other areas, and included in solvable groups, and sort of nilpotent subgroups arise very naturally. Particularly in the theory of matrix groups. So we'll see some examples in a second, but like upper triangle. So if I look at like upper triangular matrices, those are solvable. And then sort of upper triangular matrices with ones along the diagonal are nilpotent. And so these are, I mean, natural and important groups. And the nice properties of these groups gets used in classification of matrix groups. in some sense. Okay, so then there are lots of reasons looking at this, sort of the structures you get sort of just building up from abelian groups are interesting. Okay, so let's make some definitions. So the first definition, well, definition slash theorem, easy theorem. So the commutate, yeah, let me say it this way. Definition. The commutator subgroup of G, sort of written brackets G, G, is the subgroup generated by the elements GH times GH inverse for all G and H in G. Okay, so and more generally, so you write the same, you can sort of generalize this notation. Sometimes that's useful, so let me say it. So if we had two subgroups, H1 and H2, then this is just the group generated by H1, H2 times H1, H2 inverse for all H1, H2, and G. And H1 and H, capital H1, H2 and H lower 2 and capital H2. So that's what that notation means. Okay, and so when you do that for all, so when both H1 and H2 are G, you get this commutator subgroup. And what does it mean? Well, let me say simple lemma. This commutator subgroup is normal. And so I can look at, all right, G superscript ab, I'll just write it to be the quotient of G by the commutator subgroup. So this is the maximal abelian quotient. So I'll make that precise in a moment. But why do we, so this group is abelian and it's a quotient of G. And it's maximal in a sense that we'll make precise in a moment. And why is it abelian? Well, like writing GH inverse is trivial. So like that's what it means to, when you take this quotient group, well, this group is generated by these symbols GH inverse by these elements. So that means like you're forced, when you take the quotient, you're forcing all of these to become trivial. So you're sort of enforcing the relations that GH times GH inverse is equal to E, but that just means GH, sorry, everywhere I wrote, and GH times GH inverse is trivial. This should have been the other way of multiplying them. Sorry. So it should be GH times the quantity HG inverse. So then I get GH is equal to HG, just multiplying this out. So all this is. So GAB is an abelian group, but it's an easy to check. in any map from G to H, where H is the abelian group. So here, I mean, by map, I mean a group homomorphism, factors through. Let me say factors uniquely through GAB. So usually we write that kind of thing as we have the natural map from G to GAB, just the projection onto this coset, the space of cosets. And so I mean, this is the universal property of this GAB. So the maximal abelian quotient is sort of a group satisfying this universal property that any map from G to an abelian group factors through GAB. So this GAB is also called the abelianization of G. And what we've just shown is that, and what's easy to show is that this explicit construction like gives you a group satisfying this universal property. And so you can sort of take, and probably it's better to take, so being more consistent with my polemics the first week, it's probably better to take the definition of the abelianization to be sort of via this universal property, and then to just sort of observe that this gives you a construction of the abelianization. Either way, and today we're going to do more things with commutators, so that's why I put the emphasis on the commutator subgroup itself. Okay, so that's something. Let me not say more about that right now, but okay, so yes, let me go back to our motivation. And we want to look at groups that can be built up from abelian groups in some sense. And so like this sort of starts to study that, because you're saying, okay, like if I have a group G, like I'm looking at like what is the largest abelian group that it surjects onto. Is another way to think about this. So GAB is sort of the largest abelian group it surjects onto. But then you can sort of repeat this process. So we have this exact sequence, G mod G to G to GAB. So this is a normal subgroup. And this is abelian. Well, then we could ask, like, what happens if we repeat this process? And now we've sort of broken up G into two parts, this abelian group and this commutator subgroup, and then there's some extension between them. So, and this notation just means this arrow is a surjection, and this arrow is an injection, which identifies sort of this subgroup with the kernel of this map. So the image of this map is the kernel of this map. So just another way to write down that G mod, the commutator subgroup is GAB. But I guess that should be familiar. And this notation should be familiar probably from last term when you were discussing homological algebra or modular theory. Okay. So if we want to take an arbitrary group G and then just try, like if we want to try and break it down into abelian parts, what we can do is we can just repeat this. So let me give this subgroup a name. So I'll call this G, right notation. I think this is the notation Dubbin and Foote uses. So we'll call this G, then upper parentheses 1 equals G. Then let me call sort of G upper parentheses 2 the commutator subgroup of G1. And then in general, I mean, you're going to say Gi plus 1 is just a commutator subgroup of Gi, Gi. So what that looks like is we have this group G, and then we have a normal subgroup of it, G1. And we have a normal subgroup, G2, and so on. And this chain sort of goes off forever to the left. And well, each of these subgroups, like if I take the sort of quotient at each step, I get an abelian group. So Gi mod Gi plus 1. That's just G of I mod its commutator subgroup. So that's just the abelianization of Gi. This is an abelian group. Okay, and so let me make the definition then. G is solvable if there exists some I greater than 0 such that Gi, so this G sub I, or G superscript parentheses I, is just the trivial subgroup. Okay, but then what that means, I should have, so maybe I should do 2 parts in this definition. So this should probably actually be the second part of this definition. Let me just give these groups a name. So these groups Gi, they're called, for the sequence of groups Gi, this is called the derived or commutator series of G. So it's the sequence of groups G parentheses 1, G parentheses 2, and so on, you get by just repeating this commutator construction. So this is called the derived or commutator series of G. And then 0. And then a group is solvable if this sort of chain of subgroups like eventually terminates with the identity element. So there's some finite step after which you just land at only the trivial subgroup. And so here, this is an exercise on your homework to show that this statement is equivalent to like the following. So this is the same as saying there exists any chain. So trivial group is equal to the first, let me say it this way, H0, which is normal in H1, which is normal in H2, which is normal in HM, which is equal to G, such that G mod, such that HI mod H I minus 1 is abelian. So this is the notion, and this is basically what you should think when you say a group built up out of abelian groups by this sort of extension process. Like to get H1, so like to get H1, or sorry, to get H2, so if we take the abelian subgroup H1, and sort of the quotient H2 mod H1, which is also abelian, and so we put them together and we get this thing, and then we sort of put that together with something else abelian to get a new thing, and so on, all the way until we've built up G itself. So this commutator series of G is just sort of a canonical way to do it, sort of the best. Chain GI is the best possible way to do this, or maybe like the shortest possible way to do this. So there's a canonical way, and for any group, there's a canonical way to sort of try and write it like this, and that canonical way is the commutator. And like any other way you try to do it, will sort of, I mean, somehow we'll have to refine this commutator sequence in some sense. So just for example, like, so if I look at the last step, so like HM mod HM minus 1, that's an abelian quotient of G, like if I have one of these. And so that means HM minus 1, so that means HM minus 1 sort of contains the commutator subgroup. So, okay. Well, anyway, you can think about this, and this is an exercise in your homework assignment to sort of check carefully that these two conditions are equivalent. Okay, but good. So this is the definition of solvability. It's just literally something you can build up from abelian subgroups. And then there's this canonical way to do it using the derived series, which is useful sometimes either, like for example, for proving things about solvable groups, it's sort of useful to have a canonical way to get such a chain. But also, yeah, it can be useful for other things too to have this idea. Okay, good. So that's solvable. Let me scroll back to the diagram we had at the top. So, and the problem with solvable groups is maybe that they're just a little too, well, actually, you know what? Let's do an exercise before we get any further. So why don't you compute the derived series for S3. So let me just give you 5 minutes to think about this. Okay, so let me just write down the answer and then I'll ask someone to explain it to me. And there are a couple of different ways you can think about it. So the zero, yes, I don't think I wrote this up here, so let me add this. And typically you start these at 0 and you say G0 is equal to G. So the 0 thing is just S3. And then inside of that, we have first derived subgroup, S3, 1, and so on. Okay, and so this, then this is just equal to S3. This one's equal to A3. This one is just trivial. And that continues. So as soon as you hit the trivial group, like the commutator of the trivial group is just the trivial group again. So as soon as you hit the trivial group, you sort of stay where you are forever. And more generally, it's always true that like if you start with a finite group, like S3, then like at some point, you can't like at some point you're not going to get any smaller because like you have a decreasing sequence of integers that are all at least one. So at some point the sequence has to stabilize. So you always have sort of maximal solvable quotient is another way to say that. Just by sort of going until the derived series terminates. And sort of you're solvable when sort of like when the derived series terminates, it hits the identity element. But some groups, the derived series terminates at some other subgroup. Like non-solvable groups, it has to terminate at some other subgroup. Okay, good. So, in fact, maybe, yeah, well, I'll say that in a second, actually. So good. So, does anyone want to explain this computation to me? Or maybe let me rephrase, could I convince anyone to explain this computation to me? Great. Yeah, good. Yeah, good. Thanks, Sandra. So yeah, so if you just express sort of these brackets, like you see that these, and if you start with two permutations, well, when you do this commutator of these two permutations, you get and you get H twice at H and H inverse. So those are give you an even permutation. Yeah, and you anyway. So you get an even permutation because so the number of transpositions in H is the same as the number of transpositions in H inverse. So that gives you an even number, and same for G and G. So you get an even permutation. So that means this derived subgroup is inside of A3 because it's generated by even permutations. But now, in fact, it has to be all of A3 because A3 is just Z mod 3Z. It's generated by a single 3 cycle. And well, we know the commutator can't be the trivial group because you can check that S3 is not an abelian group. So that's the idea. So it can't be trivial because S3 is abelian. Let me just note there's another way to see. Yeah, well, actually, let me ask, can someone tell me a different way to see that the commutator subgroup has to be contained in A3? Well, that's true, but S3 is a normal subgroup. So there are groups whose commutator subgroup is the group itself. So you have to give some argument to show that it's not the whole group, like that the commutator subgroup is not S3. So does anyone have a different argument you can give, or maybe which is really just a different way of saying the same argument? Okay, so I won't torture you guys. So let me just say it. So another way you can think about this is you can say you have a map from S3 to Z mod 2Z. Given by the sign. Okay, and so, well, usually I write this group, let me say it this way, because I think this is how I wrote before. The group plus or minus 1 under multiplication, which is just sort of a different way to write the cyclic group of order 2. This is a map to an abelian group. This is a group homomorphism from S3 to an abelian group. So its kernel contains the commutator subgroup. So, and this is something I said probably out loud earlier, but let me just remind you what this means. I mean, this is just another way to say that S3 mod its commutator is the maximal abelian quotient. And that means if I have any map from S3 to an abelian group, then the kernel contains the commutator subgroup. But the kernel of the sign of the sign map is just A3. So by definition. So this is sort of another way you can say this argument that's maybe a little bit more, this is something that's a little bit easier to generalize to other groups. So maybe this is, but it's just another way to say that this commutator has to be inside of A3. So and this is a good, remember, like if you're ever computing the derived series of a group and you know that group has a map to some abelian group, then like you automatically the commutator subgroup has to be in the kernel of that map. Let me do another related example. So I started to talk about, I almost started to talk about nilpotent groups. Let me just shift around how I was going to do this lecture. So let me do one more example related to this example, just so you can see a different phenomena. Then I'll say just a couple more properties about solvable groups, and then we'll take a break, and then we'll come back and talk about these nilpotent groups that I mentioned. So here's the other example. Well, let me just do the same thing for S5. So I have S5, 0, S5, 1, and so on. And so well, the first one's S5, and then the derived subgroup is actually going to be A5 again. So it's going to be the alternating group. And then the derived subgroup of the alternating group is going to be the alternating group too. And then the derived subgroup of that is, again, well, it's still the alternating group. So this is an example where you start with a group and you do its derived series, but and it has to stop somewhere, but where it stops is not the identity. So S5 is not solvable. And so why, and let me just say out loud why this is. I mean, again, using the sign map, but now for S5, we see that the commutator subgroup is contained in A5, but it's a normal subgroup of A5, and A5 is simple, so it's either the trivial subgroup or the whole thing. And well, it can't be trivial because S5 is not abelian, so it's the whole thing. So the commutator subgroup is A5, but now the commutator subgroup of A5 is a normal subgroup of A5. A5 is not abelian, so it has to be the whole group again. So because A5 is simple, its commutator subgroup is equal to A5. Let me just make the following note. If G is simple and not abelian, then G brackets G, the commutator subgroup of G, which is also called G parentheses 1, is equal to G itself. So same argument I just gave for A5 works for any simple group G that's not abelian. And if it's abelian, then the commutator subgroup is just the trivial subgroup. Okay, good. So that's another example. So let me state one nice property of commutator subgroups. G is a group, then H is a normal subgroup of G, then, well, saying G is solvable is the same as saying both H and G mod H are solvable. So this is nice. Probably as Dean sort of, if you start with solvable groups and try to build new groups, like you're going to stay in the category, like you're going to stay with solvable groups. So you can't sort of put together solvable groups in such a way that you get something not solvable. So, I mean, one way to think about this is, and like you could imagine you live in a world where you started with abelian groups and then you sort of started to put those together, like by taking extensions of abelian groups, and you got this thing called solvable groups. But then you could sort of repeat this process by putting together solvable groups by extensions and get something new. Like, so you can a priori imagine such a world exists. But this is saying that doesn't exist, like that's not the world. So if you start with abelian groups, you can get the solvable groups, and that's sort of as far as you can get by sort of putting abelian groups together. You can't sort of take solvable groups and then like put them together in a different way to get something not solvable. That's sort of what this says. So and another way to think about solvable groups is they're sort of, the category of solvable groups is the largest subcategory of the category of all groups, which contains abelian groups and sort of satisfies this closure under extension property. So that's a nice way to think about. So that's a nice structural way to think about solvable groups that sort of generalizes. Like that's a nice structural way to think about it in the sense that like this is an idea you sometimes want to employ in other categories. Like you want to sort of take some set of nice things and then like look at sort of the smallest subcategory that contains all of those and is contained and is like closed under extension. Okay, so that's a nice property of solvable groups. And this doesn't hold, for example, for nilpotent groups or abelian groups. So this holds for solvable groups, but not sort of the other classes we're looking at. And then we do two nice results, or just state two nice results. So first is Burnside's theorem. If the order of G is equal to P to the A, Q to the B, for sort of P and Q prime, then G is solvable. Good, and then, oh, sorry, I just saw the chat from earlier. Sorry, I missed that earlier. Okay, but anyway, so Burnside's theorem says if you have a group whose order is a product of sort of two prime powers, then it's solvable. Or if G is a group whose order is only two prime factors, then it's solvable. So that's pretty remarkable. I mean, this is some vast generalization of some of the things we did before. Like, so we saw like a group of order. Well, yeah, I guess I didn't say this, but we'll say it. Yeah, let me say it after. We essentially saw the group of P power order, like a P group is solvable. I'll come back to this after our break. We saw like that you could classify groups of order PQ by just looking at, and sort of, you can classify groups of order PQ and you can sort of always end up getting them as semi-direct products. So if you think about sort of some of the exercises we did in examples we did in class, that follows pretty quickly from them. So like this is definitely true for a group of order P times Q. But then I am proving it for groups of order P to the A times Q to the B. Like that's a lot more. So this is sort of an impressive theorem. And we'll actually, hopefully we'll come back to this in sort of the rep theory section. So it turns out you could use some representation theory to give a nice proof of this theorem. Let me state an even harder, a much harder theorem. This is the Feit-Thompson theorem. which says if G, the order of G is odd, then G is solvable. We put an exclamation point. I mean, somehow, if you don't know any group theory, like this is, well, if you only know a little bit of group theory, like this is really remarkable. Like if you've thought about examples of groups before, this stuff's like, if you've thought about lots of examples of groups before, like this maybe gets a little less remarkable, because I mean, if you start thinking about examples of groups and classifying groups, you see that sort of, and things can sometimes get much more complicated once two is in play. And this proof is very, very long. I don't know anything about how it's actually proved. I don't know what techniques go into it, but this is like one of the main steps. This is one of the, I guess, the main, well, again, I don't know anything about this, so I shouldn't say this confidently, but my understanding is that like this is one of the main conceptual steps, or like one of the main steps in proving the classification of simple groups. So like in particular, this tells you that simple groups are going to have even order. Like non-abelian simple groups will have even order. Okay, so but yeah, we're not, and we won't say anything more about that during the rest of the class. And you're not allowed to use this statement. You're not allowed to use this statement like on homework. This is unless you turn in like the full 400-page proof with it. I don't know if we'll ever need it, but okay. Anyway, I don't know that it would ever be useful, but anyway. Okay, so let's take a break. Let's break till 1:30, and I'll come back and say just a few things about nilpotent groups. Okay, so get started again. So I'm going to say something about nilpotent groups. And again, if you look at our diagram at the start, nilpotent groups live between abelian groups and solvable groups. So their nilpotent groups are in particular solvable, but somehow they have a nicer structure theorem, at least for finite nilpotent groups. So they're a little bit closer to like abelian groups in that way, and that like finite abelian groups have a nice structure theorem. And they're characterized by a different property it's a different property that's useful in some cases. So it's just another useful class of groups that rises that's a little bit more special than solvable groups. Okay, so what is a nilpotent group? Well, and there are different ways to think about them. One way to think about them is like looking at this construction we did of the derived series, and then like thinking about like different ways you could sort of make sort of canonical chains of normal subgroups, or canonical chains of subgroups where sort of the quotients are abelian. And sort of there are two other ways to do this. Let me sort of say the one that's closest to this first. So let me define G0 is equal to G. So now superscripts, but no parentheses. So G1 is going to be equal to the commutator subgroup. G2 is going to be the commutator not of G1 with itself, but of G with G1. So it's all the things you get by sort of taking commutators of elements in G and elements in G1. Then and so on. So Gi is just the commutator of G with Gi minus 1. Okay, so and this is, so let me note. So yeah, let me call, and this is the lower central series. And like it's related to the derived series in that G naught, well, the first two terms are the same. The first term is just G itself, so 0, and that's the same. And then in G1 is equal to G parentheses 1. They're both just the derived subgroup. But in general, so for I greater than equal to 1, for I greater than equal to 2, we have just that this lower central series subgroup contains the derived subgroup. That should be, yeah, that's okay. Well, let me say it this way. So the lower central series contains derived subgroup. Yeah. Whoops, that's what I meant, right? So the quotients, like the quotients in the lower central series are still abelian, but and if the lower central series terminates, then like terminates its identity, then so does the derived series, the derived series. But like in general, sort of the lower central series can terminate without like before the derived series terminates, for example, or it can have sort of more terms in it. So somehow this is sort of, yeah, it's related to derived series, but sort of you're looking at sort of some stronger property if you ask this to terminate its identity. And so we say a group is nilpotent if G superscript I, so the is just a trivial group for I sufficiently large. And so nilpotent implies solvable. But just like as an example, well, S3 is solvable, but not nilpotent. So we already saw it was, and we already computed its derived series. But like this argument we made, like if you look at if you look at the lower central series, and we get G2. So let me write what we had before. Like G2 was A3 A3, which was trivial. So this is what we got for the derived central series. But if we look at the lower central series, then we're looking not at the commutator of A3 with A3, we're looking at the commutator of S3 with A3. And you can check that this is actually equal to A3 again. So if you sort of if you try to, like if you write down the commutator of a 2 cycle and a 3 cycle, like you don't get the trivial element anymore. Anyway, yeah, so this is a group that's solvable but not nilpotent. Good. So yeah, the point is it really is genuinely a stronger property to be nilpotent, to be solvable. And like this lower central series really can start to look different than the derived series once you sort of start looking at I greater than equal to 2. Example. So this is one characterization of nilpotent groups. There's actually an equivalent characterization where instead of building from the top, like instead of sort of going from the top down, you sort of build from the bottom up. So that's why there's a different central series called the upper central series. So here, what do? You look at the center. And like you, instead of looking at sort of the maximal abelian quotient, like you look at the center, which is sort of starting from the bottom. Like you're looking at a subgroup that sort of commutes with everything. Yeah, so like here, like in this definition, the lower central series, you're looking at sort of the commutator with everything. Like here, you're going to look at the things that commute with everything. So you're looking at Z0G, just the trivial element. Z1 of G, just the center of G. And Z2 G. Well, you look at G mapping onto, right this way. You look at G projecting onto G mod its center. And then inside of that, you have the center. So you have the center of this quotient. And that pulls back to a subgroup. So this is, you just look at the pre-image of the center of the quotient by the center. So like I said, that's a lot of words, a lot of centers. But you just keep on going. So Zi of G is just, you look at the pre-image in G of the quotient, of the center of the quotient by Zi minus 1. So this builds up, and this builds up a chain of groups sort of going from below, where the quotients are, or with normal subgroups and the quotients are abelian, and so on. That may or may not terminate at, like it will terminate, but it might not terminate at G. So it might sort of terminate as some proper subgroup. And in fact, so it turns out that G is nilpotent if and only if this chain of normal subgroups eventually hits everything. So if and only if Z sub I of G is equal to G for I sufficiently large. So this is called the upper central series because you're building up. You're sort of starting with the trivial group, subgroup, and then going larger and larger. This other one's called the lower central series because you're building down. It's not immediately obvious that there's any relation between the two, but actually it's not so hard to check in the end. That's these end up being equivalent notions. So the lower central series exhausting everything, like landing at the trivial element, ends up being really the same as the upper central series exhausting everything. So just for example, continuing S3. So we have Z0 of S3, Z1 of S3, so on. Okay, so this is definitely the trivial element by definition. And then this is the center of S3. But if you think about it, the center of S3 is just the trivial element. So nothing else in the symmetric. You just look at the formula for conjugation of permutations. Like you can always find some, like if you have to start with one permutation, there's always some other permutation that conjugates it to something else, unless you sort of had the identity permutation. So it's pretty easy to see. So in fact, this upper central series just only hits the trivial element for the, or this upper central series only hits the trivial element, the trivial subgroup, so it never gets anywhere further. Good. So And either way, though, you see that you see another way that S3 is not nilpotent. So let me just state the main classification theorem, which you can look at a proof in dominant foot if you'd like in 6.1, I think. It's not so bad. It uses techniques very similar to techniques we've used already, so it's a nice exercise to read through it. But you also don't have to. You can just take this one on faith if you like. So a finite group is nilpotent if and only if A is isomorphic the product of P1 where A is equal to, so finite group G is nilpotent where the order of G is the product of, so P sub I from I equals 1 to n, lowercase p sub I are going to be the prime factors. And then the script P sub I is just the CLO P sub I subgroup, which, so when you're in a nilpotent group, will actually be, there'll just be one. So a finite group is nilpotent if and only if for every prime factor, there's a unique CLOF P subgroup, and then you're actually just isomorphic to the product of those CLOF P subgroups. So this is like the structure, like the same thing holds for finite abelian groups, right? And just like for finite abelian groups, instead of having these CLOF P subgroups which are arbitrary P groups, you just have like abelian P groups. Like you have like Z mod P to the NZ times Z mod PZ and so on. And going the other direction is easy from what we've done so far. So going from like seeing that a group like this is nilpotent, well, if you use the second characterization in terms of the upper central series, then it follows from this exercise you guys did, where you showed that if you take a P group, then the center is always non-trivial. So if you have sort of that, you use that in the induction, sort of you quickly can see that any group that's of this form, so a product of P groups, is nilpotent. Okay, and that really gives you all of them. So in particular, well, just an example, this gives you another way you can prove the fundamental theorem of finally generated abelian groups. That's sort of, and so I've been freely using, freely using, or not, but the classification of finite abelian groups. So I've been sort of freely using the classification of finally generated abelian groups because you guys proved it last term for modules over a PID in general, and that simplifies something. That simplifies sort of things occasionally, but you could systematically go back through everything we've done and sort of eliminate anywhere we used sort of that classification and replace it with a simpler argument. And then you would still be able to prove this theorem. And then you could use this theorem to give another proof of the classification of finite abelian groups. So this is sort of another option for proving that, and probably was maybe the way it was done first. Okay, but sorry, I'll stop there, and I'll stick around if anyone has any questions.